Hello there, and welcome to the Sleepy Scientists channel. I'm so glad you found your way here tonight. Maybe the day felt long, or perhaps you simply prefer drifting off to something larger than yourself, something vast and ancient and quietly burning. Either way, you've arrived at the right place. Tonight, we're turning our attention to the star at the center of everything we know, the sun. Not as a blinding disk in the daytime sky, but as a cosmic furnace, a nuclear engine, a sphere of plasma that has been shining for longer than mountains have stood or oceans have moved. It has witnessed every sunrise that ever was, powered every breath of wind, warmed every living thing that has ever existed on this planet. And yet, for all its familiarity, the sun remains full of mysteries. You don't need to do anything right now except rest. Let your body settle. Let your mind slow. As you listen, you'll travel from the sun's blazing core to its whisper-thin corona, from the roiling convection currents beneath its surface to the solar wind streaming silently through space. You'll hear about magnetic storms and ancient flares, about the patient cycle that governs sunspots, and the long, slow death that awaits our star billions of years from now. If this kind of gentle exploration helps you unwind, if it gives you a quiet place to rest your thoughts at the end of the day, consider liking and subscribing. It helps others find their way here too, one restful night at a time. Let's begin. The sun's basic properties. The sun is not a planet. It's not a solid thing you could ever stand on. If you could somehow survive the journey and arrive at what we call the sun's surface, you would find no ground beneath you, only gas so hot it glows, plasma churning in patterns vast and slow. The sun is a ball of superheated matter held together by its own gravity, burning not with fire but with fusion, the same process that powers hydrogen bombs, but sustained, controlled, and patient. It sits on average about 93 million miles from Earth. We call this distance an astronomical unit. It's far enough that light from the sun, traveling at over 670 million miles per hour, takes just over 8 minutes to reach us. That means the sunlight touching your face right now left the sun's surface 8 minutes ago. You're always seeing the sun as it was, not as it is. A delayed broadcast from the center of the solar system. The sun is enormous by any measure we understand. Its diameter is roughly 865,000 miles. About 109 times wider than Earth. If the sun were hollow, you could fit over 1 million Earths inside it. But the sun is not hollow. It is dense, especially near the core where matter is packed together under crushing pressure. And it is massive, containing more than 99% of all the mass in the entire solar system. Every planet, every moon, every asteroid and comet, all the dust and gas scattered between the stars, all of it combined is less than 1% of the sun's mass. The sun weighs about 2 nonillion kilograms. That's a 2 followed by 30 zeros. It's a number so large it loses meaning. But its gravity is what you feel every time you stand up, every time you drop something and it falls. The sun's gravity holds Earth in orbit, keeps the planets moving in their slow and steady dance. Without it, we would drift away into the cold and the dark. The sun is made mostly of hydrogen and helium. About 73% of its mass is hydrogen, the simplest and most abundant element in the universe. Another 25% is helium. Everything else, all the heavier elements, carbon, oxygen, nitrogen, iron, gold, make up only about 2%. In astronomy, anything heavier than helium is called a metal, even though to us, oxygen and carbon don't seem metallic at all. It's a strange vocabulary, but it helps astronomers understand what stars are made of and where they came from. The Sun formed about 4.5 billion years ago from a cloud of gas and dust left over from earlier stars. When those ancient stars died, they scattered their remains into space, enriching the interstellar medium with heavier elements. Our Sun inherited those elements, and from the same cloud the planets formed. Everything on Earth, the iron in your blood, the calcium in your bones, the oxygen you breathed, all of it was once inside a star. We are made of star stuff, as Carl Sagan said. And the Sun is the star we orbit. As stars go, the Sun is unremarkable. It's classified as a G-type main sequence star, sometimes called a yellow dwarf, though it's not actually yellow and it's not particularly small. In visible light, the Sun appears white. It only looks yellow or orange when seen through Earth's atmosphere, which scatters shorter blue wavelengths and leaves the longer wavelengths to reach your eyes. In space, the Sun is white. There are stars 100 times larger than the Sun. There are stars thousands of times brighter. And there are stars so faint you would need a telescope to see them even from a few light years away. The Sun is average in size, average in brightness, average in temperature. But that ordinariness is what makes it stable, what makes it capable of sustaining life. The largest stars burn through their fuel in just a few million years and explode as supernovae. The smallest stars burn so slowly they will outlive the current age of the universe. The Sun sits in the middle, burning steadily for billions of years, giving life time to emerge, to evolve, to wonder about the star above. The Sun is about halfway through its life. It has been shining for 4.5 billion years, and it will continue to shine for another 5 billion or so. Eventually, it will run out of hydrogen fuel, swell into a red giant, and then collapse into a white dwarf, a key, fading ember cooling slowly in the dark. But that is a story for later. For now, the Sun is stable. It rises and sets with a rhythm older than civilization. It warms the air and lights the sky. It is the reason there are seasons, the reason plants grow, the reason water evaporates and falls as rain. It powers the wind and the ocean currents. It is the engine of nearly everything that happens on Earth. And it is burning, always burning, though not the way a campfire burns. There is no oxygen in the Sun's core, no combustion, no flame. The Sun shines because at its center, under unimaginable pressure and heat, hydrogen atoms are being crushed together to form helium. In that process, a tiny amount of mass is converted into energy, and that energy, released in the form of light and heat, is what keeps the Sun glowing. It is what keeps us alive. The Sun's internal structure. The Sun is not uniform. If you could slice it open and look inside, you would find layers, each with its own temperature, density, and role to play in the life of the star. These layers do not have sharp boundaries. They blend into one another gradually, the way twilight blends into night. But they are distinct enough that scientists have given them names. At the very center lies the core. This is where the Sun's energy is born. The core extends from the center to about 25% of the Sun's radius. It is small compared to the rest of the star, but it contains more than half of the Sun's total mass. Everything here is crushed together under the weight of the layers above. The pressure in the core is about 265 billion times the pressure of Earth's atmosphere at sea level. The density is over 150 times that of water. If you could take a teaspoonful of material from the Sun's core, it would weigh about 15 tons. And it is hot. The core temperature is around 15 million degrees Celsius. At that temperature, Matter doesn't behave the way it does on Earth. Atoms are torn apart, electrons are stripped away from their nuclei. What's left is a plasma, a sea of charged particles moving at incredible speeds, colliding, rebounding, colliding again. In the core, hydrogen nuclei are moving so fast that they overcome the electromagnetic force that normally pushes them apart. When two hydrogen nuclei, which are just single protons, collide with enough energy, they fuse together. Through a series of reactions called the proton-proton chain, 4 hydrogen nuclei eventually combine to form one helium nucleus. In the process, a small amount of mass is lost. That mass is converted into energy according to Einstein's famous equation, E equals mc squared. The proton-proton chain proceeds in steps. First, 2 protons collide and fuse to form deuterium, a heavy isotope of hydrogen with 1 proton and 1 neutron. This is the slowest step in the chain, the bottleneck that limits the rate of fusion. In this reaction, one of the protons transforms into a neutron, releasing a positron and a neutrino. The positron quickly annihilates with an electron, producing more energy. The neutrino, being nearly massless and interacting weakly with matter, escapes the sun almost immediately, carrying away a small fraction of the energy. Next, the deuterium nucleus collides with another proton, forming helium-3, an isotope with 2 protons and 1 neutron. This reaction releases a gamma-ray photon. Finally, 2 helium-3 nuclei collide and fuse to form helium-4, releasing 2 protons in the process. These protons can then participate in new fusion reactions. The net result is that 4 hydrogen nuclei are converted into 1 helium nucleus, 2 positrons, 2 neutrinos, and several gamma-ray photons. The energy released is staggering. Every second, the sun converts about 600 million tons of hydrogen into helium. In that process, about 4 million tons of matter are transformed into pure energy. To put that in perspective, the sun is losing mass equivalent to more than 1 million Earth masses every 150 million years. Yet this is only about 0.03% of the sun's total mass, so small that it barely affects the sun's gravity. That energy begins as gamma rays, the highest energy form of light. But the core is so dense that these gamma rays can't travel far. They are absorbed and re-emitted, scattered in random directions, absorbed again. Each time a photon is absorbed, it heats the surrounding matter. That matter then re-emits photons, but usually at a slightly lower energy, longer wavelength. Over countless absorptions and re-emissions, the high-energy gamma rays are gradually converted into lower-energy X-rays, then ultraviolet light, then visible light, and even infrared. A single photon, or rather the energy it represents, can take tens of thousands of years to travel from the core to the surface, bouncing endlessly through the layers above. Some estimates suggest it could take as long as 100,000 years or even 1 million years, depending on the exact path and the number of interactions. This is called the radiative diffusion timescale. It means that the sunlight you see today was created deep in the sun's core long before modern humans existed, before Neanderthals, perhaps even before Homo erectus. The energy has been slowly working its way outward all that time, a patient journey through the depths of the star. Meanwhile, the neutrinos produced in fusion reactions take a very different path. Because they interact so weakly with matter, neutrinos zip straight through the sun and escape into space within seconds. They pass through the radiative zone, the convective zone, the photosphere, as if none of it were there. Billions of neutrinos from the sun pass through your body every second, day and night. without you ever noticing. They are ghostly particles, messengers from the sun's core carrying information about the fusion reactions happening right now, not hundreds of thousands of years ago. Scientists can detect these neutrinos using enormous underground detectors filled with water or other materials. When a neutrino occasionally interacts with an atom in the detector, it produces a flash of light that can be measured. By studying solar neutrinos, scientists can test their models of how fusion works in the sun's core. Early neutrino experiments in the 1960s and 70s detected fewer neutrinos than predicted, a puzzle known as the solar neutrino problem. It was eventually resolved in the early 2000s when scientists discovered that neutrinos can change from one type to another as they travel, a phenomenon called neutrino oscillation. The missing neutrinos hadn't disappeared. They had simply transformed into types that the early detectors couldn't see. The core is the only place in the sun where fusion occurs. The temperature and pressure drop off rapidly as you move outward. Beyond about 25% of the sun's radius, the conditions are no longer extreme enough to sustain fusion. The energy produced in the core must somehow be transported outward through the overlying layers. In the radiative zone, this transport happens through radiation, as we've described. But radiation alone cannot carry energy efficiently through the entire star. Surrounding the core is the radiative zone. This region extends from about 25% to 70% of the sun's radius. Here, energy is transferred outward primarily through radiation. Photons move from atom to atom, gradually working their way toward the surface. The radiative zone is still incredibly hot, with temperatures ranging from about 7 million degrees Celsius at its inner edge to about 2 million degrees at its outer edge. But it is less dense than the core, and nuclear fusion does not occur here. This is a place of patience where energy creeps outward, one slow step at a time. Above the radiative zone is the convective zone. This is where the sun's interior begins to churn. The temperature has dropped enough that the plasma is no longer transparent to radiation. Instead, energy is carried upward by convection, the same process that makes water boil in a pot on the stove. Hot plasma rises toward the surface, cools and then sinks back down, creating vast circular currents. These convection cells can be hundreds of thousands of kilometers across. The convective zone is turbulent and chaotic. The rising and falling plasma creates a roiling, boiling motion just beneath the sun's surface. When you look at the sun through a telescope with the right filters, you can see this motion as granulation, a pattern of bright cells surrounded by darker lanes. Each bright cell is a column of hot plasma rising to the surface. The dark lanes are the cooler plasma sinking back down. The cells appear and disappear over the course of minutes or hours, constantly shifting, a living, breathing surface. The sun does not have a solid surface. The layer we see, the one we call the sun's surface, is the photosphere. It is simply the layer where the sun's gases become opaque, where light can finally escape into space. The photosphere is only about 500 kilometers thick, incredibly thin compared to the sun's overall size. But it is what we see when we look at the sun. The temperature here is about 5,500 degrees Celsius, much cooler than the core, but still hot enough to vaporize any metal, any rock, anything we know. Below the photosphere, energy is trapped, absorbed and re-emitted, bouncing endlessly through the layers. Above it, energy is free. Light streams outward into space, traveling at the speed of light, reaching Earth in just over 8 minutes. The interior of the sun is a place of extremes, where matter is so hot and so compressed that the normal rules don't seem to apply. And yet, out of that chaos, out of that violence, comes something steady, the light that warms your skin, the energy that powers the wind and the rain. The sun is a furnace, but it is also a gift, burning quietly in the dark, giving and giving and giving, without pause, without end. The sun's atmosphere above the photosphere, the visible surface we see, lies the sun's atmosphere. It is vast, tenuous, and strange. Unlike Earth's atmosphere, which thins gradually as you climb higher, the sun's atmosphere becomes hotter as you move farther from the surface. This is one of the great mysteries of solar physics, a puzzle that scientists are still working to solve. The lowest layer of the sun's atmosphere is the chromosphere. The name comes from the Greek word for color, because during a total solar eclipse, when the moon blocks the bright photosphere, the chromosphere appears as a thin reddish ring around the sun's edge. This reddish glow comes from hydrogen gas emitting light at a specific wavelength, a deep red color that astronomers call hydrogen alpha. The chromosphere is about 2,000 kilometers thick. Its temperature ranges from about 4,000 degrees Celsius at the bottom, where it meets the photosphere, to about 20,000 degrees Celsius at the top. This increase in temperature with height is already unusual. On Earth, the higher you go, the colder it gets. But on the sun, something is heating the chromosphere from above. In the chromosphere, the sun's magnetic field begins to dominate. Magnetic field lines emerge from the photosphere, threading through the chromosphere and out into space. These field lines can trap plasma, guiding it upward in bright, glowing loops called spicules. Spicules are jets of gas that shoot upward from the chromosphere at speeds of tens of kilometers per second, reaching heights of several thousand kilometers before falling back down. At any given time, there are tens of thousands of spicules scattered across the sun's surface, flickering in and out of existence like blades of grass, swaying in the wind. Spicules come in different types. Type 1 spicules last for about 5 to 10 minutes and reach heights of around 7,000 kilometers. Type 2 spicules, discovered more recently, are faster and shorter-lived, lasting only a few minutes, but moving at even higher speeds, sometimes reaching 100 kilometers per second or more. Both types are thought to play a role in transporting mass and energy from the photosphere into the corona, though the exact mechanisms are still being studied. The chromosphere is also home to bright regions called plages, from the French word for beaches. Plages are areas of intense emission in hydrogen alpha light, closely associated with sunspot groups and active regions. They mark locations where the magnetic field is strong and the chromosphere is heated. Plages can be much larger than sunspots, sometimes covering several % of the sun's visible disk. They are indicators of magnetic activity, and their brightness varies over the solar cycle, increasing during solar maximum and fading during solar minimum. Another feature visible in the chromosphere is filaments. A filament is a long, dark structure that appears as a dark ribbon against the bright solar disk when viewed in hydrogen alpha light. Filaments are actually prominences seen from above. They are dense clouds of relatively cool plasma suspended in the hot corona by magnetic field lines. A filament can stretch for hundreds of thousands of kilometers across the sun's surface, persisting for days or weeks. They often form along the boundary between regions of opposite magnetic polarity, where the magnetic field is complex and twisted. When a filament becomes unstable, it can erupt, rising upward and expanding outward. From the side, this appears as an eruptive prominence, a bright arc of material lifting off the sun's surface. Eruptive prominences can travel at speeds of hundreds of kilometers per second, and they often trigger coronal mass ejections as the magnetic field supporting them breaks and releases its stored energy. Above the chromosphere is a thin transition region where the temperature skyrockets. In just a few hundred kilometers, the temperature jumps from about 20,000 degrees Celsius to over 1,000,000 degrees Celsius. This narrow zone is where the chromosphere meets the corona, and it is one of the most dynamic and poorly understood regions of the Sun. The transition region is not a smooth, uniform layer. It is fragmented and variable, with different parts at different temperatures and densities. Spectroscopic observations reveal emission lines from ions at a wide range of temperatures, showing that hot and cool material are intimately mixed. The rapid temperature increase in the transition region is closely linked to the mystery of coronal heating. Something is pumping enormous amounts of energy into the corona, raising its temperature to levels far higher than the photosphere below. The transition region is where that energy deposition begins, where the relatively cool chromosphere gives way to the searing heat of the corona. And then, the corona, the Sun's outermost atmosphere. During a total solar eclipse, the corona appears as a white, ethereal halo surrounding the darkened moon. It is beautiful and ghostly, with streamers and loops extending outward for millions of kilometers. But the corona is not just beautiful, it is strange. The corona is incredibly hot. Temperatures here reach 2,000,000 degrees Celsius or more, far hotter than the photosphere below. This defies common sense. The photosphere is closer to the core where the Sun's energy is produced. The corona is farther away. It should be cooler, not hotter, and yet it blazes with heat. For decades, scientists have tried to understand why the corona is so hot. The leading theory involves the Sun's magnetic field. The field lines that thread through the chromosphere extend into the corona, and they are constantly shifting, twisting, tangling. When these magnetic field lines reconnect, releasing stored energy, they can heat the surrounding plasma. Small explosions called nanoflares happening constantly all across the Sun may be pumping energy into the corona, keeping it hot. Another possibility is that waves traveling through the Sun's atmosphere carry energy upward. These waves, generated by the churning convection below the surface, propagate through the chromosphere and dissipate in the corona, depositing their energy as heat. It may be a combination of both processes. Scientists are still investigating, using spacecraft like the Parker Solar Probe to fly closer to the Sun than ever before, measuring the temperature, the magnetic field, the flow of particles, trying to solve the mystery. The corona is not a calm place. It is threaded with magnetic field lines that loop and twist, connecting regions of opposite magnetic polarity on the photosphere. Where the magnetic field is strong and closed, the plasma is trapped, forming bright loops and arches. Where the field is open, where the field lines stretch outward into space without looping back, the plasma can escape. These regions are called coronal holes, and they appear as dark patches on images of the Sun taken in extreme ultraviolet light. Coronal holes are the source of the fast solar wind, a stream of charged particles that races outward through the solar system. The corona extends far beyond the Sun's visible edge. It fades gradually into the solar wind, which fills the entire solar system. There is no clear boundary where the Sun ends and space begins. The Sun's influence, its magnetic field, its wind, its light, reaches out to the very edge of the solar system and beyond. In the corona, the Sun reveals itself as more than just a ball of gas. It is a dynamic, magnetic, churning system, constantly changing, constantly evolving. And the corona is where the Sun touches the rest of the solar system, where its energy and its particles stream outward, shaping the space around it. Solar activity and phenomena. The sun is not static. It does not shine with a constant, unchanging light. If you could watch the sun day after day, month after month, you would see it change. Dark spots would appear on its surface, drift slowly across the disk, and then fade away. Bright flares would erupt, releasing energy in minutes that equals the output of 1,000,000 atomic bombs. Vast arcs of plasma would rise from the surface and hang suspended in the corona before collapsing back down or being flung into space. These are the phenomena of solar activity, and they are driven by the sun's magnetic field. The most familiar sign of solar activity is sunspots. Sunspots are dark patches on the sun's surface, cooler than the surrounding photosphere. While the average temperature of the photosphere is about 5,500 degrees Celsius, sunspots are only about 3,500 degrees. They appear dark not because they are cold, but because they are cooler by comparison. If you could see a sunspot by itself, isolated from the rest of the sun, it would still glow brightly enough to hurt your eyes. Sunspots form where the sun's magnetic field is particularly strong. The field lines emerge from the photosphere in tight bundles, and the intense magnetic field inhibits the flow of hot plasma from below. This keeps the sunspot cooler than its surroundings. A typical sunspot has a dark central region called the umbra, surrounded by a lighter striated region called the penumbra. The largest sunspots can be tens of thousands of kilometers across, large enough to swallow Earth whole. Smaller sunspots, called pores, can be just a few hundred kilometers wide. Sunspots often appear in pairs or groups. They tend to have opposite magnetic polarities, with one spot acting as a magnetic north pole and the other as a south pole. The magnetic field lines arch from one spot to the other, forming loops in the corona. These loops can trap hot plasma, creating bright, glowing structures visible in ultraviolet and X-ray images. Sunspots are not permanent. They appear, grow, shrink, and fade over days or weeks. A large sunspot group might last for a month or more, while a small pore might disappear in a few hours. As the sun rotates, sunspots drift across the visible disk. The sun rotates faster at the equator than at the poles, a phenomenon called differential rotation. At the equator, the sun completes one rotation in about 25 days. At the poles, it takes closer to 35 days. This differential rotation twists and stretches the sun's magnetic field, helping to create the complex patterns of sunspots and solar activity. Where there are sunspots, there is often more dramatic activity. Solar flares are sudden, intense bursts of energy that occur near sunspot groups. A flare can release as much energy as 1 billion megatons of TNT, all in the span of minutes or hours. The energy comes from the sun's magnetic field. When magnetic field lines near a sunspot become twisted and stressed, they can suddenly snap and reconnect in a process called magnetic reconnection. The energy stored in the field is released in a violent explosion. Flares emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The high-energy radiation from a flare can reach Earth in just 8 minutes, traveling at the speed of light. When it strikes Earth's upper atmosphere, it can ionize atoms and disrupt radio communications. Strong flares can even interfere with GPS signals and power grids. Coronal mass ejections, or CMEs, are even more dramatic. During a CME, the sun hurls a massive cloud of plasma and magnetic field into space. These clouds can contain billions of tons of material and travel at speeds of hundreds or even thousands of kilometers per second. Unlike flares, which release energy primarily as radiation, CMEs involve the actual expulsion of matter from the sun. CMEs often occur in association with flares, but they are distinct phenomena. A flare is a flash of light and energy. A CME is a wave of particles and magnetic field expanding outward through space. When a CME is directed toward Earth, it can take 1 to 3 days to arrive. If the magnetic field in the CME is oriented in a certain way, it can interact with Earth's magnetic field, compressing it and triggering geomagnetic storms. These storms can create brilliant auroras, but they can also damage satellites, disrupt communications, and in extreme cases knock out power grids. Solar prominences are another striking feature of solar activity. A prominence is a large, bright loop or arc of plasma suspended in the sun's corona, anchored to the photosphere by magnetic field lines. Prominences can be enormous, sometimes stretching hundreds of thousands of kilometers into space, larger than the distance between the Earth and the Moon. They can last for days or weeks, slowly evolving, twisting, shifting. Some prominences are stable, hanging quietly above the surface. Others are eruptive, rising upward, and then suddenly breaking apart, flinging plasma into space. When a prominence erupts, it can trigger a CME. The two phenomena are closely linked, both driven by the sun's ever-changing magnetic field. Even the quiet regions of the sun's surface are not truly quiet. The photosphere is covered in granulation, a cellular pattern created by convection. Each granule is a rising column of hot plasma. The dark lanes between granules are cooler plasma sinking back down. Granules are typically about 1,000 kilometers across and last for about 10 to 20 minutes before dissolving and being replaced by new ones. At any given time, there are millions of granules on the sun's surface, constantly shifting, a restless bubbling texture. Larger structures called supergranules can also form. These are similar to granules but much larger, up to 30,000 kilometers across, and they last for about a day. Supergranules are thought to play a role in shaping the sun's magnetic field, concentrating magnetic flux at their boundaries. All of this activity, the sunspots, the flares, the CMEs, the prominences, is connected to the sun's magnetic field. The field is generated deep inside the sun by the motion of electrically charged plasma. As the plasma flows, it creates electric currents, and those currents generate magnetic fields. The sun's rotation and convection twist and stretch the field, creating the complex patterns we see on the surface. The mechanism behind this is called the solar dynamo. Deep in the sun, near the boundary between the radiative zone and the convective zone, there is a region called the tachocline, where conditions are just right for generating magnetic fields. The differential rotation of the sun, faster at the equator than at the poles, stretches magnetic field lines like rubber bands being pulled. The convective motions twist them, creating loops and tangles. Over time, these twisted field lines become concentrated into flux tubes, rope-like structures of intense magnetic field. These flux tubes are buoyant. The magnetic pressure inside them is greater than the pressure outside, so they rise, floating upward through the convective zone like bubbles rising in water. When they reach the photosphere, they break through the surface, creating sunspots. The field emerges from the photosphere in one sunspot, arcs through the corona, and returns through another sunspot with opposite polarity. This is why sunspots often appear in pairs. But the magnetic field is not static. It evolves constantly. Sunspots emerge, drift, merge, and decay. The field lines connecting them can become stretched and stressed. When the stress becomes too great, the field lines can break and reconnect, releasing the stored magnetic energy in a sudden burst. This is what happens during a solar flare or a coronal mass ejection. Magnetic reconnection is one of the most important processes in solar physics. It occurs when two oppositely directed magnetic field lines come close together and merge, forming a new configuration. The magnetic energy that was stored in the original field is released, converted into kinetic energy and heat. Particles are accelerated to high speeds. Plasma is heated to millions of degrees. This is the engine that powers flares and CMEs. Flares are classified by their X-ray brightness. The smallest flares, called A-class, are barely detectable. B-class and C-class flares are progressively stronger, but still relatively minor. M-class flares are medium-sized and can cause brief radio blackouts. X-class flares are the largest and most powerful. A single X-class flare can release as much energy as 1 billion hydrogen bombs. The largest flare ever recorded was the Carrington event of 1859, named after the British astronomer Richard Carrington, who observed it. On September 1st of that year, Carrington was projecting an image of the sun onto a screen when he saw two intensely bright patches of white light appear near a group of sunspots. The flare lasted only a few minutes, but its effects were felt around the world. The next day, a massive CME struck Earth's magnetosphere, triggering the most powerful geomagnetic storm in recorded history. Auroras were seen as far south as the Caribbean and Hawaii. Telegraph systems, the cutting-edge technology of the time, failed across Europe and North America. In some cases, telegraph operators received electric shocks. In others, the equipment continued to work even after being disconnected from batteries, powered by the electric currents induced in the wires by the geomagnetic storm. If a Carrington-scale event were to occur today, the consequences would be far more severe. Our modern world depends on electrical grids, satellites, GPS, and communication networks, all of which would be vulnerable. Power transformers could be damaged or destroyed, leading to blackouts that could last for weeks or months. Satellites could be knocked offline, disrupting communications, navigation, and weather forecasting. The economic impact could be in the trillions of dollars. Fortunately, Carrington-scale events are rare, occurring perhaps once every few centuries. But smaller geomagnetic storms are common, especially during solar maximum. Space weather forecasters monitor the sun constantly, watching for flares and CMEs that might be headed toward Earth. When a potentially dangerous event is detected, warnings are issued to power companies, satellite operators, and airlines. Astronauts on the International Space Station can take shelter in more heavily shielded areas. Satellites can be put into safe mode. Power grids can be adjusted to handle the extra load. Advance warning, even just a few hours, can make a significant difference. Understanding solar activity is not just an academic exercise. It has real, practical importance for our increasingly technological civilization. As we become more dependent on systems vulnerable to space weather, the need to predict and prepare for solar storms becomes ever more critical. And so scientists continue to study the sun, building better models, launching new missions, trying to unravel the mysteries of the solar dynamo and the processes that drive flares and CMEs. The sun is not a peaceful, unchanging star. It is active, dynamic, restless. It flares and erupts. It flings particles into space. It is a star in the full vigor of its life, burning brightly, shaping the space around it with its energy and its magnetism. And we, here on Earth, orbit within that space, bathed in its light, touched by its wind, feeling its influence in ways both subtle and profound. The sun gives us life, but it can also disrupt our technology, challenge our infrastructure, remind us that we are small and vulnerable in the face of cosmic forces. The solar cycle. If you were to count the number of sunspots on the sun every day for many years, you would notice a pattern. Some years the sun is covered with sunspots. Other years there are hardly any. This rise and fall in sunspot numbers follows a cycle that lasts about 11 years, though it can vary from as short as 8 years to as long as 14. This is the solar cycle, one of the most fundamental rhythms of the sun. The cycle begins at solar minimum, when sunspot numbers are at their lowest. The sun appears relatively calm, with few or no sunspots visible. The corona is quieter, with fewer flares and CMEs. Solar wind flows steadily from the coronal holes near the poles. This quiet period can last for months or even a year or more. Gradually, sunspots begin to appear. They emerge first at mid-latitudes around 30 degrees north and south of the solar equator. As the cycle progresses, more and more sunspots appear, and they tend to form closer and closer to the equator. This pattern, when plotted over time, creates a shape called the butterfly diagram, because the distribution of sunspots looks like the wings of a butterfly slowly closing toward the equator. At solar maximum, sunspot numbers reach their peak. The sun can have dozens or even hundreds of sunspots at once. Solar activity is intense. Flares and CMEs are frequent. The corona is complex and structured, with bright loops and arches everywhere. The solar wind becomes more turbulent, with fast and slow streams interacting and creating disturbances that ripple outward through the solar system. After solar maximum, sunspot numbers decline. The cycle winds down, returning to solar minimum. And then it begins again. The solar cycle is driven by the sun's magnetic field, which itself is generated by the motion of plasma inside the sun. The process is not fully understood, but the leading theory is called the solar dynamo. According to this theory, the sun's differential rotation, the fact that it spins faster at the equator than at the poles, stretches the magnetic field lines. Convection in the outer layers twists them. Over time, these twisted field lines create regions of intense magnetic field that rise to the surface and appear as sunspots. As the cycle progresses, the magnetic field becomes more and more tangled. Eventually, the field becomes so complex that it collapses and reorganizes. When this happens, the sun's magnetic poles flip. The north magnetic pole becomes the south pole, and vice versa. This happens around the time of solar maximum. After the flip, the field begins to rebuild in the opposite direction, and the cycle starts over. But here's the catch. It takes 2 solar cycles for the sun's magnetic field to return to its original state. The first 11-year cycle sees the field flip from north-south to south-north. The second cycle flips it back. Together, these 2 cycles make up the 22-year Hale cycle, named after the astronomer George Ellery Hale, who first discovered that sunspots are magnetic. Humans have been observing sunspots for centuries. The earliest definitive observations were made by Galileo and other astronomers in the early 1600s, using the newly invented telescope. Over time, astronomers noticed that sunspot numbers varied. In the mid-1800s, a German astronomer named Samuel Heinrich Schwabe analyzed decades of sunspot observations and discovered the 11-year cycle. This was a breakthrough, revealing that the sun was not constant but changed in a regular, predictable way. But the cycle is not perfectly regular. Some cycles are strong, with many sunspots and intense solar activity. Others are weak. Some last longer than others. Predicting the strength and duration of the next cycle is difficult. Scientists use computer models, historical data, and observations of the sun's magnetic field to make forecasts. But the sun often surprises them. There have been periods in history when the solar cycle seemed to shut down entirely. The most famous is the Maunder minimum, a period from about 1645 to 1715 when sunspots almost disappeared. During those 70 years, very few sunspots were observed, and the few that did appear were small and weak. This period coincided with a time of cooler temperatures in Europe, a period sometimes called the Little Ice Age, though the connection between low solar activity and cold climate is still debated. Since the Maunder minimum, the solar cycle has resumed its regular rhythm. We are currently in solar cycle 25, which began in December 2019. The exact peak of this cycle is expected sometime around 2025, though it's hard to say precisely when solar maximum will occur until after it has passed. The solar cycle affects more than just sunspots. It influences the entire sun. During solar maximum, the corona is bright and complex. The solar wind is more variable. Space weather is more active. During solar minimum, the corona is simpler, with long, stable streamers. The solar wind is steadier. Fewer geomagnetic storms occur. For those of us on Earth, the solar cycle matters. It affects the frequency of auroras, the intensity of radiation in space, the risk to satellites and astronauts. It may even have subtle effects on Earth's climate, though this is still an area of active research. The solar cycle is a reminder that the sun is not a static object in the sky. It is a living, changing star, with rhythms and moods. It grows active, then quiet, then active again. And this cycle has been going on for billions of years, long before there was anyone to watch it. And it will continue long after we are gone. The solar wind and heliosphere. The sun does not keep its energy to itself. It radiates light, yes, but it also emits something else, something more material. A wind. Not a wind of air, but a wind of particles, a stream of charged atoms flowing outward from the sun's corona, racing through the solar system at hundreds of kilometers per second. This is the solar wind. The solar wind is made mostly of electrons and protons, the building blocks of hydrogen atoms torn apart by the intense heat of the corona. There are also alpha particles, which are helium nuclei and trace amounts of heavier ions. These particles are so hot, moving so fast, that they escape the sun's gravity entirely and stream outward into space. There are two types of solar wind, slow and fast. The slow solar wind flows at about 300 to 400 kilometers per second. It comes from regions near the sun's equator, from the streamer belt, where the corona is dense and the magnetic field is complex. The slow wind is denser than the fast wind, carrying more particles per cubic meter, but it is also more variable, with gusts and lulls. The fast solar wind, on the other hand, flows at 600 to 800 kilometers per second. It comes from coronal holes, the dark regions in the sun's atmosphere where the magnetic field is open, where field lines stretch outward into space instead of looping back to the surface. The fast wind is less dense but steadier, blowing constantly like a cosmic gale. As the solar wind travels outward, it carries the sun's magnetic field with it. The field lines rooted in the photosphere are stretched and twisted by the sun's rotation and the outward flow of the wind. The result is a spiral pattern, like the spray from a rotating garden sprinkler. This is the interplanetary magnetic field, and it fills the solar system, connecting the sun to the planets. The solar wind does not blow forever. Eventually, far from the sun, it slows down. At a distance of about 80 to 100 astronomical units, roughly 80 to 100 times the distance from the Earth to the sun, the solar wind meets the interstellar medium, the thin gas between the stars. The pressure from the solar wind is balanced by the pressure from outside. The wind slows abruptly, piling up like water hitting a wall. This boundary is called the termination shock. Beyond the termination shock is a region called the heliosheath, where the solar wind is still flowing but much more slowly, turbulent and mixed with particles from interstellar space. And beyond the heliosheath is the heliopause, the boundary where the solar wind finally stops, where the sun's influence ends and true interstellar space begins. The heliopause is not a sphere. It is more like a teardrop or a bubble, compressed on the side facing the sun's motion through space and stretched out on the other side. The exact shape depends on the pressure of the interstellar medium and the strength of the solar wind. Only two human-made objects, Voyager 1 and Voyager 2, have crossed the heliopause and entered interstellar space. They sent back data showing that the boundary is sharp, a clear transition from the solar wind to the interstellar medium. Together, the sun, the solar wind, and all the space they influence make up the heliosphere. The heliosphere is like a protective bubble around the solar system, shielding the planets from most of the galactic cosmic rays, high-energy particles from distant supernovae, and other violent events in the galaxy. Without the heliosphere, Earth and the other planets would be bathed in far more radiation. The solar wind interacts with the planets in different ways. At Earth, the wind encounters the magnetosphere, a magnetic shield generated by our planet's iron core. The solar wind compresses the magnetosphere on the side facing the sun and stretches it out into a long tail on the night side. The magnetosphere protects us, deflecting most of the solar wind around the planet. But some particles slip through, especially during geomagnetic storms, when a strong gust of solar wind or a CME strikes. These particles spiral down along Earth's magnetic field lines toward the poles, where they collide with atoms in the upper atmosphere and create auroras, the northern and southern lights. Planets without magnetic fields like Mars and Venus are hit directly by the solar wind. Over billions of years, the solar wind has stripped away much of Mars's atmosphere, leaving it thin and cold. Venus, with its thick atmosphere, has fared better, but it too loses some of its atmosphere to the sun's relentless wind. The solar wind is not constant. It varies with the solar cycle, with the sun's rotation, with the emergence and decay of sunspots and active regions. During solar maximum, the wind is more turbulent, with more CMEs and faster streams interacting, creating shocks and disturbances that ripple outward through the heliosphere. During solar minimum, the wind is steadier, though still not perfectly smooth. The solar wind is invisible. You cannot see it or feel it, but it is there, always flowing outward from the sun, filling the space between the planets, connecting everything in the solar system to the star at its center. It is a river of particles, a current in the void, and we live within it. The sun's influence on Earth, it is hard to overstate how much the sun shapes our world. Every breath you take, every step you walk, every green thing that grows, all of it depends on the sun. The sun is the engine that drives Earth's climate, its weather, its seasons. It is the source of nearly all the energy that flows through the biosphere. Plants capture sunlight through photosynthesis, converting light energy into chemical energy stored in sugars. Those sugars feed the plants themselves and every animal that eats them. Herbivores eat plants, carnivores eat herbivores, and so the energy flows upward through the food chain, all of it ultimately derived from the sun. Fossil fuels, coal, oil, and natural gas are ancient sunlight, energy captured by plants and algae millions of years ago and stored in the earth. Even the wind and the rain are driven by the sun. The sun heats the equator more than the poles, creating temperature differences that drive atmospheric circulation. It evaporates water from the oceans, which rises, cools, and falls as rain. The water cycle, the wind, the ocean currents, all powered by the sun. Without the sun, Earth would be a frozen, lifeless rock. The average temperature on Earth is about 15 degrees Celsius. Without the sun's warmth, the temperature would plummet to near absolute zero, the coldest possible temperature. The oceans would freeze solid. The atmosphere would condense and fall as snow. Nothing we recognize as life could survive. But the sun's influence is more than just heat and light. The sun also affects Earth through space weather, the changing conditions in the space around our planet caused by solar activity. Space weather includes solar flares, CMEs, and variations in the solar wind. When these phenomena reach Earth, they can have real and sometimes dramatic effects. Solar flares, as we discussed earlier, emit intense bursts of radiation. The high-energy X-rays and ultraviolet light from a flare reach Earth in about 8 minutes. When they strike the upper atmosphere, they ionize atoms, creating extra layers of charged particles. This can disrupt high-frequency radio communications, especially over polar regions where the signals have to pass through the ionosphere. Aviation and maritime industries, which rely on radio for communication and navigation, can be affected. GPS signals, which travel through the ionosphere, can also be degraded. CMEs, when directed toward Earth, can cause geomagnetic storms. These storms occur when the cloud of plasma and magnetic field from a CME interacts with Earth's magnetosphere. If the magnetic field in the CME is oriented opposite to Earth's field, the two can reconnect, allowing energy and particles to flow into the magnetosphere. This compresses and distorts the magnetosphere, inducing electric currents in the upper atmosphere and on the ground. Geomagnetic storms can be beautiful. They create auroras, glowing curtains of light in the polar skies. The auroras are caused by charged particles from the solar winds spiraling down along Earth's magnetic field lines and colliding with oxygen and nitrogen atoms in the atmosphere. Oxygen emits green and red light, nitrogen emits blue and purple. The result is a shimmering, dancing display, one of the most beautiful natural phenomena on Earth. But geomagnetic storms can also be dangerous. The electric currents induced in the ground can flow through power grids, causing transformers to overheat and fail. In severe cases, this can lead to widespread blackouts. In March 1989, a powerful geomagnetic storm caused a blackout in Quebec, Canada, leaving millions of people without power for hours. Satellites in orbit can also be affected, with their electronics damaged by radiation, or their orbits altered by increased atmospheric drag during storms. The sun also sends out high-energy particles, solar energetic particles or SEPs, during flares and CMEs. These particles, mostly protons, can reach Earth in minutes to hours. For astronauts in space or on the moon, SEPs pose a radiation hazard. Even at the altitudes where airplanes fly, radiation levels can increase during solar storms, a concern for frequent flyers and flight crews. Over longer timescales, the sun's influence on Earth's climate is more subtle and still not fully understood. The sun's total energy output, its luminosity, varies slightly over the solar cycle, increasing by about 0.1% from solar minimum to solar maximum. This is a small change, but over many cycles it could have cumulative effects. Some scientists have suggested that long-term variations in solar activity, such as the Maunder minimum, might influence Earth's climate. However, the evidence is mixed, and most climate scientists agree that human-caused greenhouse gas emissions are the dominant factor driving current climate change. Still, the sun's role in shaping Earth's climate over geologic time is clear. Early in Earth's history, the sun was about 30% less luminous than it is today. This is known as the faint young sun paradox, because with a dimmer sun, Earth should have been frozen. And yet, geological evidence suggests that liquid water existed on Earth's surface as far back as 4 billion years ago. The explanation is likely that Earth's early atmosphere contained much more greenhouse gases, which trapped heat and kept the planet warm despite the fainter sun. As the sun has brightened over billions of years, Earth has had to adjust. The amount of carbon dioxide in the atmosphere has gradually decreased, compensating for the increasing solar luminosity and keeping the planet habitable. This delicate balance, maintained by geological and biological processes, has allowed life to persist. The sun gives, but it also takes. In about 1 billion years, the sun will be about 10% brighter than it is today. This increase will trigger a runaway greenhouse effect. The oceans will begin to evaporate. Water vapor, a powerful greenhouse gas, will trap more heat, causing more evaporation. Eventually, Earth will lose its oceans entirely. The water vapor will be broken apart by ultraviolet light in the upper atmosphere, and the hydrogen will escape into space. Earth will become a dry, barren world, much like Venus is today. But that is still 1 billion years away. For now, the sun is our constant companion, rising every morning, setting every evening. It lights our days and warms our world. It is the reason we are here. And even as we explore space, even as we dream of traveling to other stars, the sun remains the center of everything we know. Sabrim, the sun's past. The sun has not always existed. There was a time about 4.6 billion years ago when the space where the sun now shines was dark and empty, or nearly so. It was a region within a giant molecular cloud, a vast expanse of gas and dust drifting between the stars. The cloud was cold, only a few tens of degrees above absolute zero, and it was mostly hydrogen, with traces of helium and heavier elements left over from earlier generations of stars. Something disturbed the cloud. Perhaps a nearby supernova, a dying star exploding in a violent burst, sent a shockwave rippling through the cloud. Or perhaps the cloud simply became dense enough in one region that gravity took over. Either way, a small part of the cloud began to collapse. As the cloud collapsed, it began to spin, conserving angular momentum. The spinning caused it to flatten into a disk, with most of the mass falling toward the center. The center grew hotter and denser as material piled up, compressed by the weight of the layers above. This was the protostar, the infant sun glowing faintly with the heat of gravitational contraction. For about 10 million years, the protostar continued to collapse, growing hotter and denser at its core. The surrounding disk of gas and dust fed the growing star, and within that disk, the planets began to form. Small grains of dust stuck together, forming larger and larger clumps. These clumps collided and merged, growing into planetesimals, asteroid-sized bodies that eventually became the planets we know today. Finally, after 10 million years, the temperature and pressure at the core of the protostar reached a critical threshold. Hydrogen nuclei began to fuse into helium. Nuclear fusion had ignited. The protostar became a star. The sun was born. The young sun was different from the sun we see today. It was dimmer, only about 70% as luminous. Its surface was more active, with larger and more frequent sunspots, intense flares and a powerful solar wind. The sun's rotation was faster too, completing one turn every few days instead of the month it takes now. The rapid rotation and vigorous convection generated a stronger magnetic field, which drove more violent solar activity. Over time, the sun calmed down. The intense solar wind carried away angular momentum, slowing the sun's rotation. As the rotation slowed, the magnetic field weakened, and solar activity became less extreme. The sun settled into a stable state, fusing hydrogen in its core, radiating energy steadily outward. This is the main sequence, the long, stable phase of a star's life. The sun has been on the main sequence for the past 4.5 billion years, and it will remain there for another 5 billion or so. During this time, the sun has been slowly brightening. As hydrogen fuses into helium in the core becomes denser and hotter. The increased temperature speeds up the fusion reactions, causing the sun to produce more energy. Over the past 4.5 billion years, the sun's luminosity has increased by about 30%. This gradual brightening will continue for the rest of the sun's main sequence life. The early Earth had to contend with a dimmer sun. As mentioned earlier, this is the faint young sun paradox. The evidence suggests that Earth had liquid water, and perhaps even life as far back as 4 billion years ago. How could this be possible with a sun only 70% as bright as today? The answer lies in Earth's atmosphere. Early Earth likely had a thick atmosphere rich in greenhouse gases like carbon dioxide and methane, which trapped heat and kept the planet warm despite the fainter sun. As the sun brightened, Earth's atmosphere changed. Carbon dioxide was gradually removed from the atmosphere, absorbed by oceans and locked into rocks through geological processes. This natural thermostat helped keep Earth's temperature relatively stable even as the sun grew brighter. Life itself may have played a role, with photosynthetic organisms producing oxygen and altering the composition of the atmosphere. The sun's past is intimately tied to Earth's past. The energy from the sun drove the formation of the atmosphere and the oceans. It powered the first chemical reactions that led to life. It shaped the climate, the weather, the cycles of day and night. The sun has been a silent witness to the rise and fall of countless species, the slow drift of continents, the growth of mountains, the carving of valleys. It has seen the Earth change from a barren, molten world to a blue-green planet teeming with life. And the sun, too, has changed. It is brighter now, more luminous, more settled. It is a mature star, middle-aged, steady. It has burned for longer than the Earth has existed, and it will continue to burn for billions of years to come. But its past is a reminder that nothing lasts forever. Not even stars. The sun was born from a cloud of gas and dust, and one day it will die, returning its matter to the cosmos, enriching the interstellar medium so that new stars can form. The cycle continues, endless and vast. The sun's future. Everything ends, even stars. The sun, which has shone for 4.5 billion years, will not shine forever. Its fuel is finite, its life is long, but not infinite. In about 5 billion years, the sun will exhaust the hydrogen in its core. When that happens, the delicate balance between gravity pulling inward and fusion pushing outward will be broken, and the sun will change. But this end is not sudden. The sun's journey toward death is gradual, marked by distinct phases, each lasting millions or hundreds of millions of years. Understanding this timeline requires understanding how stars evolve, how they age, how they transform as their fuel runs out and new fusion processes begin. The changes will be slow at first. As the hydrogen in the core runs low, the fusion reactions will slow down. The core will begin to contract under its own gravity. As it contracts, it will heat up. The contraction releases gravitational energy, which heats the core and the surrounding layers. Eventually, the temperature will rise enough that hydrogen in a shell around the core, a region that hasn't yet fused, will ignite. This shell burning will release even more energy than core fusion did. At first, this shell burning is weak and does not dramatically change the sun's appearance. But over tens of millions of years, as the inert helium core grows larger and heavier, the shell burning intensifies. The extra energy will push outward on the sun's outer layers, causing them to expand. The sun will swell, growing larger and larger. Its surface will cool, shifting from white to yellow to orange to red. The sun will enter what is called the subgiant phase. During the subgiant phase, the sun will be noticeably different from how it appears today. Its radius will be about twice its current size, and its luminosity will be several times greater. Earth will receive more heat, and temperatures on our planet will begin to rise. But this is still not the main transformation. The subgiant phase lasts for about 1 billion years, a period during which the sun gradually but inexorably changes. Eventually, the hydrogen shell burning becomes so intense and the core so compressed that the sun enters the red giant branch of stellar evolution. The sun will become a red giant, a bloated, luminous star with a cool surface and an incredibly dense core. At its largest, the sun will be enormous. Its radius will grow to about 100 times its current size, large enough to engulf the orbit of Mercury and likely Venus as well. Earth's fate during this time is one of the great uncertainties of solar evolution. Some models suggest that as the sun loses mass through its intensified solar wind, Earth's orbit will expand, allowing it to escape being swallowed. The sun could lose up to 30% of its mass during the red giant phase, and as mass is lost, the gravitational hold on the planets weakens, causing their orbits to drift outward. Other models, however, suggest that tidal forces and drag from the sun's extended atmosphere will cause Earth to spiral inward, eventually falling into the bloated star and being vaporized. Even if Earth escapes being swallowed, it will not be spared. The sun's luminosity during the red giant phase will be thousands of times greater than it is today. At its peak, the red giant sun will shine with a luminosity about 2,500 times its current value. Earth's surface will be scorched, its temperature rising to over 1,000 degrees Celsius, hot enough to melt lead and vaporize any remaining water. The oceans, if any remain, will boil away. The atmosphere will be stripped. Earth will become a molten, lifeless ball of rock, orbiting a dying star in a system that no longer resembles the one that nurtured life for billions of years. But long before the sun becomes a red giant, Earth will already be uninhabitable. In about 1 billion years, the sun's increasing luminosity will trigger a runaway greenhouse effect. The sun is slowly getting brighter, about 10% every billion years, as the core becomes denser and hotter. This gradual brightening, which has been happening throughout the sun's life, will eventually push Earth past a critical threshold. At some point, perhaps in 800 million to 1 billion years, the sun will be bright enough that Earth's oceans will begin to evaporate faster than they can be replenished by rainfall. Water vapor will fill the atmosphere, and because water vapor is a greenhouse gas, it will trap more heat, causing more evaporation. This positive feedback loop will run away, eventually causing all of Earth's water to evaporate. The water vapor will be broken apart by ultraviolet light in the upper atmosphere, and the hydrogen will escape into space, lost forever. Earth will lose its oceans, its blue skies, its clouds. It will become a desert world, dry and dead, similar to Venus is today. So even before the sun's transformation into a red giant, life on Earth will have ended. Any species that survives that long, if humanity or its descendants are still around, will have had to leave Earth long before the red giant phase begins. Meanwhile, as the sun expands into a red giant, strange things will happen in the outer solar system. Jupiter and Saturn, currently frozen giants wreathed in clouds of ammonia and methane, will warm up. Their icy moons, Europa, Ganymede, Enceladus, Titan, will thaw. For a brief time, perhaps a few 100 million years, these moons might have liquid water on their surfaces or beneath thin ice shells. They might even become habitable, at least by microbial life. Titan, with its thick atmosphere and abundance of organic molecules, could become especially interesting. But the window will be short. As the sun continues to evolve, even these distant moons will be baked, their atmospheres stripped, their water lost. The red giant phase is unstable. The sun's outer layers will puff up and then contract, pulsating. Strong stellar winds will blow, carrying away mass. The sun will lose a significant fraction of its total mass, perhaps 30% or more, expelled into space in a slow, steady wind. This mass loss is crucial. It determines how much mass the sun will have when it finally settles down as a white dwarf, and it affects the orbits of any surviving planets. The mass loss occurs because the sun's outer layers, now far from the core, are only weakly bound by gravity. The intense radiation pressure from the luminous core, combined with pulsations and shocks in the atmosphere, can lift material off the surface and push it into space. The wind during the red giant phase is much stronger than the solar wind today, perhaps 1,000,000 times more intense. It blows steadily outward, gradually removing the sun's outer envelope. Inside the sun, the core continues to collapse. It is now made mostly of helium, the ash left over from billions of years of hydrogen fusion. The core grows hotter and denser, compressed by its own gravity. For a long time, nothing else happens. The core is inert, not fusing, just contracting. The temperature rises, but it's not yet hot enough to ignite helium fusion. Eventually, after millions of years of contraction, the core reaches a temperature of about 100 million degrees Celsius. At this temperature, helium nuclei can fuse. 3 helium nuclei combine to form a carbon nucleus in a process called the triple alpha process, so named because helium nuclei are also called alpha particles. This releases energy, but less energy than hydrogen fusion did. The triple alpha process is much more sensitive to temperature than hydrogen fusion. A small increase in temperature causes a large increase in the fusion rate. Helium fusion begins suddenly in an event called the helium flash. In a matter of seconds, the core releases a tremendous burst of energy, as much as the entire Milky Way galaxy emits in the same time. The power output is staggering, equivalent to about 100 billion times the sun's current luminosity, but this energy is absorbed by the overlying layers and doesn't escape the sun. The helium flash is invisible from the outside. An observer watching the sun would see no outward sign that anything dramatic had just happened deep in the core. The helium flash occurs because the core is in a special state called degeneracy. In degenerate matter, the pressure is provided not by the thermal motion of particles but by quantum mechanical effects. Electrons are packed so tightly together that the Pauli exclusion principle, which states that no 2 electrons can occupy the same quantum state, prevents them from being compressed further. This degeneracy pressure supports the core against gravity, even though the core is not hot enough to fuse. When helium fusion ignites in a degenerate core, the sudden release of energy heats the core, but the degeneracy pressure doesn't change because it doesn't depend on temperature. This means the core doesn't expand, which would normally cool it down and regulate the fusion. Instead, the higher temperature causes the fusion rate to skyrocket, producing even more energy, which raises the temperature further, causing more fusion, and so on. This runaway process is the helium flash. It continues until the core becomes hot enough that thermal pressure takes over from degeneracy pressure. At that point, the core expands, the temperature drops, and the runaway is halted. The entire process takes only a few seconds, but it fundamentally changes the structure of the star. After the helium flash, the sun stabilizes briefly. It shrinks from its red giant size, settling into a smaller, hotter configuration. It burns helium in its core for about 100 million years, a brief respite compared to the billions of years it spent burning hydrogen. During this phase, the sun is on what astronomers call the horizontal branch of the Hertzsprung-Russell diagram, a plot of stellar luminosity versus temperature. While helium fuses in the core, hydrogen continues to fuse in a shell around the core. The sun now has two sources of nuclear energy, the helium core and the hydrogen shell. The interplay between these two sources creates a complex and changing structure. But helium, like hydrogen, is finite. When the helium in the core runs out, the core contracts again. The helium ash, now carbon and oxygen, forms an inert core. A shell of helium burning forms around the carbon-oxygen core, and above that, a shell of hydrogen burning continues. The sun expands once more, this time becoming an even larger red giant, though not quite as large as before. This phase is called the asymptotic giant branch, or AGB, because on the Hertzsprung-Russell diagram, the star's evolutionary track approaches the red giant branch asymptotically. The AGB phase is chaotic. The sun pulsates, expanding and contracting with a period of hundreds or thousands of days. Thermal pulses occur, sudden bursts of energy from the helium-burning shell that caused the sun to brighten dramatically, and then fade. These pulses are caused by the helium shell burning, becoming unstable. Helium accumulates in the shell from the hydrogen burning above. When enough helium builds up, it ignites suddenly, producing a burst of energy. This energy pushes outward, temporarily shutting off the hydrogen burning above and disrupting the star's structure. After the pulse fades, things settle down, and the cycle begins again. With each thermal pulse, more material is expelled into space. The solar wind, already strong, becomes a gale, blowing away the outer layers of the sun at speeds of tens of kilometers per second. Over the course of a few 100,000 years, the sun will lose most of its remaining mass. The envelope, the outer layers that once made up most of the star, will be gone. What's left is the core, now exposed, a tiny hot ball of carbon and oxygen about the size of the Earth, but with about half the sun's original mass. This is a white dwarf, the remnant core of a star that has exhausted its nuclear fuel. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh about 15 tons. The matter is packed so tightly that electrons are degenerate, providing the pressure that supports the white dwarf against gravity. Unlike normal stars, white dwarfs do not have an internal source of energy. They do not fuse anything. They simply shine from the residual heat left over from their formation. The expelled material, the outer layers blown away during the AGB phase, will form a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. The name comes from early astronomers who thought these nebulae looked like the disks of planets when viewed through small telescopes. From a distance, a planetary nebula looks like a glowing shell or ring surrounding the white dwarf. The light from the white dwarf, now incredibly hot, over 100,000 degrees Celsius, ionizes the gas, causing it to glow in brilliant colors. Reds from hydrogen and nitrogen, greens from oxygen, blues from helium. Planetary nebulae are some of the most beautiful objects in the sky, delicate, symmetrical, ephemeral. They come in many shapes: rings, hourglasses, butterflies, spheres, each one unique, shaped by the interplay of the dying star's winds, its magnetic field, and perhaps the presence of a companion star. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, all are planetary nebulae created by sun-like stars at the end of their lives. But the planetary nebula will not last. Over tens of thousands of years, it will expand and fade, dispersing into the interstellar medium, and the white dwarf will remain alone, cooling slowly in the dark. A white dwarf does not burn. It has no fusion, no source of energy. It shines only from the residual heat left over from its formation. Over billions, even trillions of years, it will radiate that heat away, growing dimmer and cooler. Eventually, it will become a black dwarf, a cold, dark ember, invisible in the void. This is the sun's future. From a glowing protostar to a stable main sequence star, from a bloated red giant to a tiny white dwarf, and finally to a black dwarf. A journey spanning billions of years, a life cycle shared by billions of other stars in the galaxy. But that future is far away. For now, the sun is stable, burning steadily, warming Earth, lighting the sky. It is halfway through its life, in its prime, reliable and constant. We orbit a star in the full vigor of its existence, and we are fortunate to live in this time, when the sun is neither too young and violent nor too old and dying, but just right. Studying the sun, humans have been watching the sun for as long as there have been humans. Ancient cultures tracked its motion across the sky, marking the solstices and equinoxes, using the sun to tell time and to guide the planting of crops. They built monuments aligned with the rising or setting sun on specific days of the year, like Stonehenge in England or the Temple of Kukulkan in Mexico. The sun was often worshipped as a god, a giver of life, a symbol of power and constancy. In ancient Egypt, the sun was Ra, the king of the gods who sailed across the sky each day in his solar bark and journeyed through the underworld each night. In ancient Greece, it was Helios, driving his chariot of fire from east to west. The Aztecs knew it as Tonatiuh, who demanded sacrifice to continue his daily journey. Across cultures, across continents, the sun was sacred, revered, feared. People understood instinctively that their lives depended on it, even if they didn't understand what it was or how it worked. But understanding the sun, truly understanding what it is and how it works, required the development of science. For most of human history, the prevailing view was that the sun orbited the Earth. This geocentric model, championed by ancient Greek astronomers like Ptolemy, was the accepted wisdom for over 1,000 years. It wasn't until the 1600s that Nicholas Copernicus proposed a heliocentric model, placing the sun at the center of the solar system with the Earth and other planets orbiting it. This was a revolutionary idea, and it took decades for it to be accepted, aided by the observations of Galileo Galilei and Johannes Kepler. The invention of the telescope in the early 1600s allowed astronomers to see sunspots for the first time. Galileo, Thomas Harriot, Christoph Scheiner and others observed dark spots on the sun's surface and noted that they moved, showing that the sun rotates. Galileo used sunspot observations to estimate the sun's rotation period, finding that it took about a month for a sunspot to travel across the visible disk and return to the same position. For a long time, it wasn't clear what sunspots were. Some thought they were planets passing in front of the sun. Others thought they were openings or holes in the sun's bright surface, revealing a darker interior. It wasn't until the 1800s that scientists began to understand that sunspots were features on the sun itself, regions that were cooler than the surrounding surface. In the 1800s, astronomers began to study the sun's spectrum, the rainbow of colors produced when sunlight is passed through a prism. In 1814, a German optician named Joseph von Fraunhofer discovered dark lines in the spectrum, hundreds of them, scattered throughout the rainbow. These Fraunhofer lines, as they came to be called, were mysterious. Fraunhofer catalogued them, labeling the strongest ones with letters, but he didn't know what caused them. The explanation came decades later. In the 1850s and 60s, physicists Gustav Kirchhoff and Robert Bunsen showed that each chemical element produces a unique pattern of bright lines when heated to incandescence and absorbs light at those same wavelengths when cooler gas is placed in front of a bright background. The dark lines in the sun's spectrum, Kirchhoff realized, were absorption lines caused by elements in the sun's atmosphere absorbing specific wavelengths of light emitted by the hotter photosphere below. By studying these lines, scientists could determine what elements are present in the sun. They found hydrogen, iron, calcium, sodium, magnesium, and many others. This technique, called spectroscopy, revolutionized our understanding of the sun and the stars. For the first time, humans could analyze the chemical composition of objects millions or billions of kilometers away, simply by studying the light they emit. One element was discovered in the sun before it was found on Earth. In 1868, during a total solar eclipse, astronomers observed a bright yellow line in the sun's chromosphere that didn't match any known element. The French astronomer Jules Janssen and the British astronomer Norman Lockyer independently discovered this line. Lockyer suggested that it came from a new element, which he named helium after Helios, the Greek sun god. For nearly 30 years, helium was known only from the sun. It wasn't until 1895 that helium was isolated on Earth, extracted from a uranium mineral by the Scottish chemist William Ramsay. In 1904, George Ellery Hale discovered that sunspots are magnetic, the first detection of a magnetic field beyond Earth. Hale used a spectroheliograph, an instrument that allowed him to photograph the sun in the light of specific spectral lines. He observed that spectral lines from sunspots were split into multiple components, a phenomenon known as the Zeeman effect, which occurs in the presence of a strong magnetic field. This was a major breakthrough, showing that magnetism plays a fundamental role in solar activity. Over the following decades, scientists developed theories to explain how the sun generates its magnetic field. The leading theory, the solar dynamo, suggests that the field is created by the motion of electrically charged plasma inside the sun, particularly in the convective zone and near the boundary with the radiative zone. The differential rotation of the sun, combined with the churning convection currents, stretches, twists, and amplifies the magnetic field, creating the complex patterns we see on the surface. Understanding how the sun produces energy was another major challenge. In the 1800s, scientists knew that the sun radiated enormous amounts of energy, but they didn't know where that energy came from. Some suggested that the sun was burning like a giant coal fire, but calculations showed that chemical combustion could only power the sun for a few thousand years, far too short compared to the geological evidence that Earth was millions or billions of years old. Others proposed that the sun was contracting under its own gravity, converting gravitational potential energy into heat. This could power the sun for about 20 million years, better than chemical burning, but still not nearly long enough. the discovery of radioactivity in the late 1800s led to new ideas. Perhaps the sun was powered by radioactive decay, but this too was insufficient. The true answer came in the early 1900s with the development of nuclear physics. In 1920, the British astronomer Arthur Eddington suggested that the sun's energy might come from the fusion of hydrogen into helium. Albert Einstein's famous equation E equals mc squared showed that even a small amount of mass could be converted into a tremendous amount of energy. If the sun could fuse hydrogen, it could shine for billions of years. But how exactly did fusion work? In 1938, the German physicist Hans Bethe worked out the details of the proton-proton chain, the series of nuclear reactions that fuses hydrogen into helium in stars like the sun. For this work, Bethe was awarded the Nobel Prize in Physics in 1967. The 20th century brought new tools for studying the sun. Rockets and satellites allowed astronomers to observe the sun in wavelengths of light that don't reach Earth's surface, like ultraviolet and X-rays, which are absorbed by the atmosphere. These observations revealed the hot corona, the solar wind, and the violent phenomena of flares and CMEs. Space-based observatories could watch the sun continuously, without the interruptions of day and night or the distortions of Earth's atmosphere. One of the most important solar observatories is the Solar and Heliospheric Observatory, or SOHO, a joint mission of NASA and the European Space Agency launched in 1995. SOHO orbits the Sun at the first Lagrange point, or L1, a point between the Earth and the Sun where the gravitational pull of both balances, allowing the spacecraft to remain in a fixed position relative to the Sun. From this vantage point, SOHO has observed the Sun continuously for over 25 years. SOHO has made countless discoveries. It has discovered over 4,000 comets, more than any other observatory, by watching for small objects that pass close to the Sun. It has studied the Sun's interior using helioseismology, which analyzes oscillations on the surface caused by sound waves bouncing through the Sun's interior. These oscillations reveal information about the Sun's internal structure, rotation, and temperature, much like seismologists use earthquakes to study Earth's interior. SOHO has monitored solar activity, tracking sunspots, flares, and CMEs, providing data that has helped scientists understand the solar cycle and predict space weather. Another key mission is the Parker Solar Probe, launched in 2018 and named after the American astrophysicist Eugene Parker, who first proposed the existence of the solar wind in the 1950s. Parker Solar Probe is designed to fly closer to the Sun than any spacecraft before it, diving through the corona to measure the temperature, the magnetic field, and the solar wind. The spacecraft will eventually reach within about 4 million miles of the Sun's surface, closer than the orbit of Mercury, where temperatures outside the spacecraft can exceed 700 degrees Celsius. To survive these extreme conditions, Parker Solar Probe is equipped with a thick carbon composite heat shield that faces the Sun, protecting the delicate instruments behind it. The spacecraft's observations are helping scientists understand the mysteries of coronal heating and solar wind acceleration. Why is the corona so hot? How does the solar wind reach such high speeds? These are fundamental questions in solar physics, and Parker Solar Probe is providing the data needed to answer them. The Solar Dynamics Observatory, or SDO, launched in 2010, takes images of the Sun every few seconds in multiple wavelengths, creating an almost real-time view of solar activity. SDO's data has revolutionized our understanding of solar flares, CMEs, and the Sun's magnetic field. By watching the Sun in extreme ultraviolet light, SDO can see the corona and track the evolution of active regions, the sudden explosions of flares, and the ejection of CMEs. The images are stunningly detailed, revealing the intricate structure of the Sun's atmosphere. There are also ground-based solar telescopes, which have the advantage of larger apertures and the ability to be upgraded with new instruments. The Daniel K. Inouye Solar Telescope in Hawaii, which began operations in 2020, is the largest solar telescope in the world, with a primary mirror 4 meters across. It can resolve features on the Sun's surface as small as 30 kilometers, capturing incredible detail of sunspots, granulation, and magnetic structures. The telescope is equipped with advanced adaptive optics, which correct for the blurring effects of Earth's atmosphere, allowing it to achieve resolution comparable to space-based telescopes. All of these observations from space and from the ground have taught us an enormous amount about the Sun. We know its composition, its structure, its age. We understand how it generates energy through nuclear fusion in its core. We know how that energy is transported outward, first by radiation, then by convection. We understand the solar cycle driven by the Sun's magnetic field. We can predict solar activity, forecast space weather, and protect our technology from solar storms. But there is still much we don't know. Why is the corona so hot? This is one of the biggest mysteries in solar physics. The photosphere is about 6,000 degrees Celsius, but the corona is 2 million degrees or more. Heat normally flows from hot to cold, so the corona should be cooler than the photosphere, not hotter. Something is pumping energy into the corona, heating it to extreme temperatures. The leading theories involve magnetic reconnection and wave heating, but the exact mechanisms are still being debated and studied. How exactly does the solar dynamo work? We know that the Sun's magnetic field is generated by the motion of plasma inside the Sun, but the details are complex and not fully understood. How does differential rotation create the sunspot cycle? Why does the cycle last 11 years, and why does its strength vary from one cycle to the next? These are active areas of research. What triggers flares and CMEs? We know that magnetic reconnection releases energy, but what causes the magnetic field to become unstable in the first place? Can we predict when a flare or CME will occur before it happens? Improving space weather forecasting requires a better understanding of these processes. How will the Sun's activity change in the future? Will the solar cycle continue as it has for centuries, or might it weaken or shut down, as it did during the Maunder minimum? What would that mean for Earth's climate? These are questions that scientists are still working to answer, using observations, computer models, and theoretical studies. The Sun is close, the closest star to us, but it is also complex and dynamic. Studying it requires patience, advanced technology, and a willingness to accept that there are still mysteries to solve. Every new observation, every new mission brings us a little closer to understanding our star. And in understanding the Sun, we learn about all stars, about how they live and die, about the forces that shape the universe. The Sun is both familiar and strange, both ordinary and extraordinary. A cosmic laboratory, just 8 light minutes from home. Closing reflections, the Sun is ordinary. By the standards of the universe, it is not particularly large or bright or unusual. It is one star among hundreds of billions in the Milky Way galaxy, and the Milky Way is one galaxy among hundreds of billions in the observable universe. There are stars larger, hotter, more massive. There are stars smaller, cooler, more long-lived. The Sun is average, unremarkable, common. And yet, the Sun is everything to us. It is the reason we exist. It is the warmth on your face, the light that fills the sky. the energy that flows through every living thing. It is the gravity that holds the solar system together, the force that keeps the Earth in its orbit, spinning steadily through space. Without the sun, there would be no Earth, no life, no us. We are children of the sun. Our planet formed from the same cloud of gas and dust that formed the sun. Every atom in our bodies was once part of that cloud, forged inside earlier stars and scattered into space when those stars died. The oxygen we breathe, the carbon in our cells, the iron in our blood, all of it came from stars. And the energy that powers our bodies, the food we eat, the warmth we feel, all of it comes from the sun, either directly or indirectly. The sun has been there for every moment of human history. It rose over the first humans walking the plains of Africa. It shone on the builders of the pyramids, the philosophers of ancient Greece, the explorers sailing across unknown seas. It has witnessed every triumph and every tragedy, every act of kindness and every act of cruelty. It does not judge. It simply shines, constant and indifferent, a witness to everything, and it will outlive us. Long after humanity is gone, whether we destroy ourselves or evolve into something unrecognizable, or spread to the stars, the sun will still be there, burning quietly in the dark. It will continue its slow march toward death, growing brighter, swelling into a red giant and finally fading into a white dwarf. The sun's story will end as all stories do, but not yet. Not for a long, long time. For now, the sun is our companion. It rises every morning, dependable and familiar. It lights our days and marks the passage of time. It is so constant that we rarely think about it, so ordinary that we take it for granted. But every now and then, on a quiet morning or a peaceful evening, it's worth pausing to remember that the sun is not just a light in the sky. It is a star, a vast, ancient nuclear furnace, burning with the energy of millions of atomic bombs every second, holding us in its gravity, bathing us in its light, giving us everything we need to live. We orbit within the sun's influence, and we always will. Wherever we go, however far we travel, the sun will always be the star we came from. It is home, and perhaps as you drift off to sleep tonight, you can carry that thought with you. That somewhere in the dark, the sun is still shining, that it will rise again tomorrow, as it always has. That it is there, patient and eternal, a glowing ember in the vastness of space, a small star in an enormous universe. And for us, everything. Thank you for listening. If these calm, cosmic explorations help you find rest at the end of the day, consider subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Sleep well.